Alright, this is a work/energy problem here. It's primarily work, but go from there. We basically have a 70-degree slope. We have a 10 kilogram box on it, and that 10 kilogram box is 30 centimeters above a spring. The slope has a coefficient of friction of 0.1, and the spring constant is 50 newtons per centimeter. Per centimeter's key there. Okay, so let's really notice that. We want to know how far the block is going to come down the spring. We want to know how far it's going to bounce back up. All right, so ultimately, we know that the energy is going to be conserved both by gravity and by the spring, but not by the friction, because friction is a non-conservative force. So our height, or our bounce back, is going to look something like 0 equals work of gravity minus the work of friction. That's what we're ultimately looking at. So we got to figure out the work of friction as it drops down and bounces back. Now, to get there, we're going to have to take an intermediate step. Okay, because remember, as it bounces back, it's not just going to stop at 30 centimeters and bounce back up. There's still going to be friction as it hits the ground. So we're going to deal with that in a second here. So we have the force parallel of gravity is 9.8 times 10 times sine of 70, or 95.9. The force perpendicular is 9.8 times 10 times cosine 70 equals 20.4. Okay? Force of friction, therefore, is 20.4 times 0.1 equals 2.04. Alright, so to get how far it's going to slide down before it starts coming back up, we have to consider the force of friction, the force of the spring, and the force of gravity. What we know is that the work done, the net work done, or the change in kinetic energy is going to be 0, because it's starting at rest, and when it gets right at the bottom, it's going to be at rest. So we have 0 times, or 0 equals 95.9 times 0.3 plus x. That's how much energy is going to, that's how much work is going to be done, because that's the distance, 0.3 plus the compression, x, is going to be the work done by the spring. We have minus 2.04 times 0.3 plus x. Okay, that's friction. Okay, it's going to travel that same distance. And then we add on minus 1/2 times 5,000 x squared. Okay, that's 5,000, which is in newtons per meter, which is what we wanted in. And this is the amount of work done by a spring. So we can do all that. We can do all the math there, everything like that. But it's going to come out that x is equal to 0.127. That's the compression of the spring. Now what that means is that we now know how far it's going to travel down and then back up. Remember, the spring is a conservative force. Okay, so when we're talking about this, we need to consider the spring, because what it's going to look like is work done by gravity minus the work done by friction, and then you're going to have plus the work of the spring minus the work of the spring. It's even the same going down as it is up. So we can just say, cancel each other out. Alright, so for this, alright, I'm going to have to erase a little bit here to give us some room. Okay, again, we know that x is 0.127. That's key. Okay. We know the work done by gravity is going to be 95.9 times 0.3 plus 0.127, right? So it's going down. Then it's going to come back up, which is minus 0.127, okay? And then minus x, where x is now the bounce back height. X is no longer the spring drop, it's now the bounce back height. And that's going to be plus or minus the force of friction, which is 2.04 times 0.3 plus 1.27 plus 1.27 plus x. Okay, because it's friction's going down into the spring, back up the spring, and then back as it's bouncing up. It's always all there. This should simplify out to be 27.6 minus 95.9x minus 2.04 x, and we get x equals 0.28 meters or 28 centimeters. So that's how much it's going to bounce back up. So its height on the bounce back is going to be 2 centimeters lower than it started out at. Okay, and all that energy is going to be lost to friction.